All right, let's do this. This is 7.5, the unit circle approach. So in this section, really nothing new other than learning periodic properties. So the first 3 pages of these notes is going everything we have learned for the past 3 sections. How to find the 6 trig ratios given a point on the terminal side of an angle or given a point on the unit circle. So today's about finding the 6 trig ratios given a point on the unit circle. So what you see down below, to translate all of this into English, says no matter how you travel on the unit circle, whether you travel in a positive direction or whether you travel in a negative direction, it doesn't matter how many revolutions you do, but doesn't matter how many revolutions you do, because no matter where you stop, at that exact point, you can find the 6 trig ratios. That's all this is saying with all the fancy stuff above. So no matter where I stop on the unit circle, doesn't matter where, I can find the 6 trig ratios of this point given as the point AB. Okay. So like I said, nothing really new today, because when you correlate, so these are going to have the sine function of t. T represents the units you have traveled around the unit circle and when you have stopped. So that's all that means, sine of t. So if you ever see sine of t, you're finding the 6 trig ratios of a point on the unit circle. Okay, to sum that up. So sine of t, well, remember, if we're given a point, sine always relates itself to the y value of the point. So sine of t would be b, and cosine of t would be a. So sine of some distance traveled t would be b, and cosine of t would be a. So this is all we have to really worry about. Given a point on the unit circle, no matter what distance you have traveled around it, you can find the 6 trig ratios functions of that given point. Sine is b, cosine of t is a, and then you wouldn't even need to look at the point for the rest of them. Tangent would put sine over cosine, so tangent puts b over a. Cosecant is the reciprocal of sine, so that'd be 1 over b. Secant is the reciprocal of cosine, so that would be the reciprocal of a, 1 over a, and cotangent is the reciprocal of tangent, so a over b. That's it. Nothing crazy. You could even say it didn't even need to be a rotation on the unit circle. We could have just said, all right, here's my unit circle, here is my triangle, and then our point here is AB, where this would be A, that would be B, and you could still find all of these ratios based on that. Once again, nothing new, just reiterating everything. Because in math, repetition is key. Okay, so let's try it out. We're given a point on the unit circle, -1/2 and square root of 3 over 2. Find the 6 trig functions that correspond to t. Fair enough. Let's start. We'll start with cosine. Oh. Cosine of t. Cosine relates to the x value of the given coordinate. So this would be -1/2. Then sine of t relates to the y value of that given coordinate. So square root of 3 over 2. Then tangent puts sine over cosine, right? It'll put these coordinates over each other. So sine we'll put square root of 3 over 2 over negative 1/2. Multiply by the reciprocal, and we're going to get negative square root of 3. Okay, perfect. So there's the first three. Now we know the reciprocal functions. So cosine's reciprocal function is secant. So secant of t would just be negative 2. And then sine of t, the reciprocal function is cosecant of t, which would be 2 over the square root of 3, or rationalized 2 square root 3 over 3. And then cotangent is the reciprocal function of tangent. So we just take the reciprocal of negative square root of 3, which would be negative 1 over the square root of 3, or negative square root 3 over 3. There it is. That's it. And that's given some random point on the unit circle. You can still find the 6 trig functions of that given point. Okay. Do it again. Given the points square root of 5 over 3 and 2 over 3, find the 6 trig functions. So cosine of t square root 5 over 3. Sine of t is 2/3. Tangent of t, put sine over cosine. So 2/3 over square root 5 over 3. Multiply by the reciprocal. 2/3 times 3 over the square root of 5. And cancel, cancel. You get 2 over the square root of 5, or 2 square root 5 over 5. Now all that's left is the reciprocal functions. Cosine's reciprocal function is secant. Secant of t is going to be 3 over the square root of 5. But again, rationalize. 3 square root 5 over 5. Sine of t's reciprocal is cosecant of t. So we'll just get 3/2. And then tangent is cotangent of t, and cheat codes. Step 1 back, flip that, and we're good. Square root 5 over 2. Great, right? Okay. And once again, no matter where a point travels on the unit circle, positive or negative revolutions, wherever that point lands, no matter the distance traveled, you can find the 6 trig ratios of that given point. Which again, is nothing new to us. We know how to find the ratios of the 6 trig functions given a point on the terminal side, given a point, or given a point on the unit circle. Which is what 7.5 wants us to know again. Next page. Trigonometric functions of any angle. So this says that, what do we have? Values of the trigonometric functions of an angle are determined by the coordinates of the point P, AB, on the unit circle corresponding to theta. The units used to measure the angle theta are irrelevant. Well, that's fun. So to find the exact value of a trig function of an angle theta requires that we locate the corresponding point on a given circle whose center is at the origin. So for an angle theta in standard position, let P equal the point AB be a point on the terminal side of an angle that is also on the circle x squared plus y squared equals r squared. Basically our unit circle, right? Or any circle with radius r. And your given ratios are, look at this, sine is b over r, cosine's a over r. So what we're saying here is that, once again, if I have my coordinate plane drawn and I have my angle in standard position, they say let this point be AB given this value of theta, and if you put it together, you can make your right triangle where the base is A, the height is B, and the hypotenuse is going to be considered R. So, and based on this right triangle, you can find your 6 trig ratios. Like I said, nothing new today. Just doing repetition. Okay. So, find the exact values of the 6 trig functions given an angle theta if -1, -1 is a point on the terminal side. So, go ahead and draw your coordinate plane. And then -1, -1, what quadrant does that belong to? -1, -1 has to be in quadrant 3, where everything's negative, right? So down here is going to be our right triangle. Here's theta. And the base is -1. The height is -1, because that's the point we're going off of, right? That's 1, -1, which means our hypotenuse, using Pythagorean theorem, should be 1 squared plus 1 squared, so we should get 2. So our hypotenuse should be the square root of 2. Okay. Now, based off our right triangle and our value of theta that happens to be irrelevant, because I think it's been irrelevant for these actual functions, if you're not actually calling on the unit circle, then we can say the cosine of angle theta, which puts adjacent over hypotenuse, is going to be -1 over the square root of 2, or negative square root of 2 over 2. And then sine of this angle theta, we'll put opposite over hypotenuse, which is going to give us the same answer as cosine. Negative square root of 2 over 2. And then tangent of theta puts opposite over adjacent, so we get 1. And now the rest is reciprocals. So secant theta will be negative square root of 2. Cosecant theta will also be the negative square root of 2. And cotangent theta will also be 1. That's it. So I guess this one's saying, I mean, it wants to say something new, but it's not, is that, okay, our point, we travel on it, we can find the 6 trig ratios of that point as long as it's on a terminal side of some given circle with a given radius. So with that being said, you can still find the 6 trig ratios and not worry about the actual angle. That's why it says the angle is irrelevant. Because what if we're not dealing with the unit circle? What if the point was -5, 5? Well, this means that the circle most likely has a radius. Well, we don't know the radius because you have to find the hypotenuse, but once you solve for it, you would get your radius. So in a sense, we're saying that you can find the 6 trig ratios on a circle with any given radius where the angle does not matter. Okay, that is something new. So that's actually cool then. I'm good with that. Other than that, it's, hey, we know how to find the 6 trig ratios. We know what those ratios are. That's it. Just follow along. Okay. Oops. All right, next. Now, this is important stuff. This is good stuff. Using periodic properties to find exact values. Okay, so your big takeaway from this lecture is to know the cycles, the periods, the revolutions of our trig functions. So to keep this really simple, as you see on the left diagram, this is a proof for sine, cosine, cosecant, and secant. So what we're saying is that if we start off with our angle of theta here, and this point AB, then to come back to this exact point, to come back to this exact terminal side, and to come back to the same exact values, it's going to take a revolution of 2 pi radians. So what we say with this is that cosine, sine, and their reciprocal functions, cosecant and secant, all repeat themselves every 2 pi. Their cycle is every 2 pi. A revolution for those functions is considered 2 pi. A period for those 4 functions is considered to be 2 pi. So like I said, I like to keep things simple. Just say that cosine, sine, secant, cosecant repeat themselves every 2 pi. That's it. They will always land on the same exact values doing a revolution of 2 pi. Okay, so that's for those 4 functions. For the last 2 functions, tangent and cotangent, well, these guys, they only repeat themselves every pi. That's it. So here we start off with our point AB, and to get to the same exact values, all we have to do is a revolution of pi, and you'll get the same exact value with doing a revolution of pi. So that's how they repeat themselves. Tangent and cotangent repeat themselves only every other pi. And more of this will come into light when we actually start graphing them, because you're like, well, why can't tangent have a revolution of 2 pi? Wouldn't it land on the same values? It sure would, but tangent and cotangent are different because they'll actually have the same exact values in a rotation of pi. They don't need a whole rotation of 2 pi to get back to the exact same value. That can't be said for cosine, sine, and tangent. Because if you look at the graph on the left, if we only did a revolution of pi, we would end down here, where doing a revolution of pi for those 4 functions would not give you the same exact value as if you did a revolution of 2 pi. So that only works for tangent and cotangent. This is why tangent and cotangent only have revolutions of pi, and this is why sine, cosine, secant, cosecant all have revolutions of 2 pi. That's it. Those are their periodic properties. Okay. So now, what was that? Eraser options. Ooh, that's cool. Okay. All right. So with that being said, if you think about what we did in the last section, I think it was, where if you were over a revolution or under a revolution, you would subtract 360 or 2 pi. Well, now, if you're dealing with tangent or cotangent, you only have to subtract pi or 180 now. The others still have to be subtracted or added by 2 pi or 360. So that's the only difference now, is that you can just subtract pi or add a pi to tangent or cotangent. So these are all still plus or minus 360 as well for all 4 of these, and these would be plus or minus 180, plus or minus 180. Okay. It wouldn't take me long to write that in there. One moment. Okay. It was coterminal angles, that's right. Okay. So now we're doing the same example as we did in the last section. It just says, find the exact value of these given trig expressions. So sine of 420 degrees, we know that is definitely over a revolution. So we would subtract 360 from it. So this would become the sine of 420 degrees minus the sine of 360 degrees, which would give us the sine of 60 degrees. And looking at your unit circle, the sine of 60 degrees is going to be, oops, square root 3 over 2. But I bet you knew that without looking at your unit circle, huh? Well, I hope so, right? Okay, next is the tangent of 5 pi over 4. Now, the tangent of 5 pi over 4 is within the unit circle. So we can be done already, but we can explore using periodic properties saying, hey, well, if I subtract the pi, am I still going to be in the unit circle? So that's what we want to practice here. So if I subtract the pi, where would I land on? So let's try that out. We would say tangent of 5 pi over 4 subtract the pi, put it over 1, and get a common denominator of 4. This now becomes the tangent of 5 pi over 4 minus 4 pi over 4, which is going to give me the tangent of pi over 4. And is the tangent of 5 pi over 4 still on the unit circle? I mean, of pi over 4 on the unit circle. And yes, there we are. So this would count as a revolution for tangent because we went pi, we subtracted a pi. Or if you add a pi, you still get back to 5 pi over 4. And no matter what, they share the same exact value. This is what it's about. Do they share the exact same value? And that answer is yes. Tangent at pi over 4 puts square root of 2 over 2 over square root of 2 over 2. And anything over itself is 1. That would be the same thing down here. Tangent at 5 pi over 4 puts negative square root of 2 over 2 over negative square root of 2 over 2. Anything over itself is 1. And negative over negative still make positive. So that is just a practice in periodic properties. That's it. Okay. Cosine of 11 pi over 4, that is definitely over a revolution. Now remember, I showed you a couple ways to solve this. You can convert it to degrees and subtract 360, or we can do our lovely, or you can count radians, or you can do our lovely little division trick, which is what I'm going to use. So we'll just say 4 goes into 11 pi, 2 pi times. This will give me 8 pi, which will give me 3 pi. So what you're left with is 2 pi plus 3 pi over 4. And this is what we care about. So this means we end up with the cosine of 11 pi over 4 becoming the cosine of 3 pi over 4. And remember, this number represents revolutions. So this means if it's 2 pi, we have done one cycle of cosine's revolution. This means that 3 pi over 4, if you do another 2 pi revolution, you end up back on 11 pi over 4. Which means they will share the exact same value, and all you have to do is look at the cosine of 3 pi over 4, which happens to be right there on the screen. And the cosine of 3 pi over 4 is going to be negative square root of 2 over 2. Not bad, right? Okay. Secant of 540 degrees, so that's definitely over a revolution. So we go ahead and subtract 360. And that's going to give me the secant of 180 degrees. Okay. Well, here's 180 degrees. Secant is the reciprocal of cosine. So if cosine is -1 at 180 degrees, the reciprocal of -1 is still -1. That's it. Nothing to it. So we really only practice the periodic properties on tangent and cosine of 11 pi over 4. Everything else is just using that coterminal angle theory where, hey, if it's over a revolution, subtract 360 or keep subtracting 2 pi or use the division trick or count radians. But now the big takeaway is just when do these functions repeat themselves? Cosine, sine, secant, cosecant repeat themselves every 2 pi. Tangent and cotangent repeat themselves every pi. That's it. And like I said, those periodic properties would probably make more sense when we start graphing. I mean, they kind of make sense when you look at the unit circle already because you see the revolutions. Like if I did do the 11 pi over 4, that would be right here, right? This means you start at 3 pi over 4, you add 2 pi, and you get back here, which becomes 11 pi over 4. So this makes the periodic properties, this makes them make sense because it says, hey, if you do 2 pi, cosine or sine or secant or cosecant will land on that angle, that same terminal side, and share that same exact value, whatever those coordinates are. That's it. Okay, that's the unit circle approach. Hey, that's in the title, right? Okay. All right. Now this one's even better. I like these ones a lot more. These are even and odd properties. So if you remember even and odd properties of algebraic functions, which maybe you do, maybe you don't, right? To be even means if you had f of negative x, you would get returned f of x. To be odd means if you had f of negative x, you would get returned negative f of x. Also, to go along with even functions, if you're even, you are symmetric with the y-axis. If you're odd, you are symmetric with the origin. Okay. Well, these are the algebraic properties for even and odd functions, and we can apply them to trig functions, which is great. So if you look at the chart, sine and cosecant, tangent and cotangent are the four odd functions. Why are they odd? Well, look at them. Sine of negative theta becomes negative sine theta. That follows the algebraic odd properties. F of negative x becomes negative f of x. So this means that sine, cosecant, tangent, cotangent are all symmetric with the origin whenever we get to graphing them. And what this also means is that cosine and secant are the only even trig functions. That's it, the only even trig functions. And why is that? Well, cosine of negative theta becomes cosine of theta. That follows the even algebraic property for trig functions. So f of negative x becomes f of x. You get the original function back. And since they're even, they are also symmetric with the y-axis. Okay, so those are the even and odd properties for trig functions, which we will see again when we graph on the next 3 sections. Lots of graphing ahead. So doing the unit circle approach, because we're not looking at graphs yet, how can we apply these even and odd properties? Well, simple enough. Just go ahead and follow the box above and use the unit circle. Sine of negative 45 degrees, since sine is odd, it can be rewritten as the negative sine of 45 degrees. And the sine of 45 degrees, or sine at 45 degrees, is square root of 2 over 2. But this negative is waiting on the outside. So our answer is negative square root of 2 over 2. It's awesome. It's just another tool to help us if we do not want to deal with negative angles. And when I say negative angles, well, where would the sine of negative 45 degrees be? There's my initial side. And negative 45 degrees would be right there. There's negative 45. And if I said, what is the sine of negative 45 degrees? Well, guess what our answer is? Right there, negative square root of 2 over 2. Exactly what we have right there. But for that answer, we didn't have to draw a diagram. We didn't have to draw the angle. We used the odd property. We brought the negative out and only had to reference the sine of 45 degrees here, which gave us the square root of 2 over 2. And we just had to apply that negative to our answer. That's it. Sometimes trigonometry is that easy, right? Okay. Cosine of negative pi. Cosine is an even function. So the cosine of negative pi becomes just the cosine of pi. And looking at our unit circle below, the cosine of pi, and even if it was negative pi, the cosine of pi is still negative 1. Okay. And then the cotangent of negative 3 pi over 2. Okay. Cotangent is an odd function, which means we can pull the negative out. So you'll get negative cotangent of 3 pi over 2. Now, look at 3 pi over 2. Look at the coordinates. Cotangent puts x over y. Cotangent puts 0 over negative 1. So that negative out front's not going to matter, right? because you'll have negative times 0 over negative 1, which just happens to be 0. Okay. Last one. Tangent of negative 37 pi over 4. Well, that's definitely over revolution, and tangent is an odd function. So we can rewrite this as the negative tangent of 37 pi over 4. And then we can use our little division trick. 4 into 37 pi. And that goes 9 pi times, which will give me 36 pi with a remainder of pi left. We end up getting 9 pi plus pi over 4. 9 pi plus pi over 4. Okay, so this means that this becomes the negative tangent of pi over 4, and tangent at pi over 4 is positive 1, but that negative's waiting on the outside, so we end up getting negative 1. Okay. And that is 7.5, the unit circle approach. The best things we learned from this section were the even and odd properties, which take with you. It's good to know that sine and cosine, all the trig functions have even and odd properties. And the periodic properties. We will be using these for graphing. We'll even use even and odd properties for graphing, that whole symmetry thing. So these last 2 pages are basically the most important. The first 3, just a refresher on everything we've learned today, or we've been learning so far, not today. Other than that, that is 7.5. Lots of graphing ahead. Exciting. See you guys at the next one.